Hey everyone, welcome back, and today we're going to be talking about something a little bit different from my usual style of videos, the second video of my calculus playlist, where today we're going to be discussing what is differentiation and what are derivatives. So before we get into the formal definition of what these major terms are in the field of calculus, let's just go ahead and take a simple function, for example, to kind of just reference this as we talk about these more advanced topics. So let's say we have the function f of x and is equal to x squared, a standard parent function for our parabola. Now we've seen x squared a lot. It's a simple parabola. If I were to graph this on my Cartesian plane, it would look something like this, right? With a domain of all real numbers and a range greater than or equal to 0. Because of course when you square a number, you can't get a negative value or a value that's less than 0. Okay, so that's a simple kind of sketch of how this graph would look like. Nothing too crazy here. Now, let's say we draw a secant line that intercepts this function at two different points, right? That's the definition of a secant line. So something like this, right? Let me just draw that a little bit better. Let's just click that. Show arrows here. And I'm going to call this secant line just, I don't know, S. It doesn't really matter. In fact, I actually won't do that. Never mind. So let's just say it intersects this function at 2 points A and B, right? Where A is the x coordinate. In fact, I'm just going to call this X. So I think it's a little bit easier. Say X. And I'll say this is actually X plus H. Now, this may look a little bit confusing at first. What is X plus H? What is X? What does it really have to do here? Okay, let's kind of talk about this. So we have X, right? That's the X coordinate of this point at point X. Pretty straightforward here. And we have X plus H, our X coordinate for this point here. What is X plus H? It's simply X plus some horizontal distance, H, whatever that may be. So let's say if X in this case was like -2, if X was -2, right? Of course, the y coordinate for this point would be f at -2, or f of x. And this right here would be, let's just say h is 5. So let's say h is equal to 5. We shift right 5 digits. Then this would be x equals 3. And we get the y coordinate to be f of 3, or f of x. Right? So pretty straightforward here. Nothing crazy. I'm not going to keep that up here. You can just pause the video for reference if you need that. But again, just know that h simply represents some horizontal distance from x, right? So what are the coordinates of these 2 points? We kind of just talked about it right now, right? Let's just kind of discuss it again. This x coordinate would be x comma f of x, right? X comma y, the output of f of x. And this would be x plus h comma f of x plus h. Let me just wrap that around a big parentheses to represent a coordinate point. Right? These are the two coordinates of this point. So let's say we wanted to calculate the slope of this secant line. Well, that's quite simple. We have 2 points, and so we simply have to use our point slope formula. If you recall, what is that point slope formula? It's simply y2 minus y1 over x2 minus x1. Pretty straightforward here. So how do we apply that to the current line to calculate its slope? Pretty simple. It would simply be y2 minus y1, so f of x plus h minus f of x, divided by x2 minus x1, which is x plus h, divided by, or rather minus x. Okay, pretty simple here. So how do we kind of demonstrate that algebraically? It'd be f of x plus h, again this is the slope for this secant line, minus f of x divided by x plus h minus x. And as you can see, these two x's actually just cancel out. And so this would be f of x plus h minus f of x of h. Okay, that's cool. That's the formula for this secant line. But let's expand onwards from there on, right? This is just some simple slope formula. What does this have to do with calculus? You'll see. Let's just say I draw another line, in this case a tangent line that again intersects this function exactly once at one point. That's the definition of a tangent line. And I'm going to actually, in fact I won't, never mind. So I'm going to have a tangent line that's going to intersect this graph at point x, right? Rather x value coordinate point x. Okay, I'm just going to call this tangent line t. Okay, so as you can see we have a secant line right here. And we have a tangent line that intersects this function y equals x squared at point x. So we already discussed how we can pretty efficiently find the slope of this secant line that intersects this function twice, but how do we find the slope of the tangent line that essentially intersects this function at exactly one point, which is x? How do we do that? Or in other words, how do we find the instantaneous rate of change at that point x, the slope of the tangent line that intersects this function at that point x? How do we know how fast the value of the function changes at this point x? How do we know that? Well, that's exactly where the derivatives come into play. Let's kind of go back to this secant line that we were talking about before. How do we kind of connect this secant line with our tangent line? Okay, so we discussed that x is a coordinate and x plus h is another coordinate that's shifted h units to the right. So h again is going to represent our horizontal distance. But what if h gets closer and closer to 0? Right? What if our horizontal distance between these 2 points gets closer and closer, or effectively minimized to hit 0? Well, okay, well, if our h was 0, then we'd simply have a tangent line again. Think about it, right? If we had x and x plus h, but h was kind of effectively hitting 0, then this h would be rendered useless. We'd have x and point x again. So we can't really do anything to find the slope of a tangent line because we only have one point. We don't have enough data to apply our slope formula to find the slope of this tangent line that hits the point, or rather hits the function at one point. In this case, it's point x, the instantaneous rate of change at point x for how much this function is increasing at that value. Okay, that's fine, but there's actually another kind of topic that we discussed that helps us find this. I was talking about how this h was effectively hitting or approaching a horizontal distance of 0 between these 2 points. Okay, so we know if we just simply said h was 0 and substituted from there, we'd go back to square one, our tangent line again. We can't do anything from that. But what if we took the limit as that horizontal distance approaches 0, as we get closer and closer to a horizontal distance of 0? Well, let's try that. So we know that, let me just redraw this function again. Okay, that was horrible. In fact, I'm just going to do this right here. Okay, so we have a secant line. It kind of goes something like this. That's great. So let's just say h is here first, or rather x plus h, and x is here. Okay, that's cool. We have an h distance of, let's just say, like 5, something like that. Let's say that we shifted h to be here. Okay, now our h value, or our horizontal distance between these 2 points, is getting smaller. Okay, what if we went over here? All of a sudden, our h distance is even less. What if we went here? What if we went here? What if we went here? What if we took the limit as that h horizontal distance approached 0, effectively kind of overlapping with this point x? Okay, let's kind of draw that algebraically. What if we take the limit as h, or our horizontal distance, approached 0? Well, that's cool, but how do we calculate the slope of that line? Well, think about it. We're still calculating the slope of our secant line, but we're just saying that the distance between our 2 coordinates, our h value, is getting closer and closer to 0. So we're still applying this same formula using these 2 coordinates. I don't know why they do that, but anyways. So we can actually kind of reuse that slope formula to get this. So we're taking the limit as the h value, our horizontal distance, approaches 0, of, again, y2 minus y1 over x2 minus x1. So f of x plus h minus f of x all over x plus h minus x. So, of course, there is a simplification here. X and negative x are going to cancel out. So let me get my eraser out. Again, this new UI is kind of weird here. Tough to get it adjusted to. So this would just be h. So theoretically, this is still the slope formula for our secant line. Again, hitting the point at exactly, or rather the function at exactly 2 points. But we're taking the limit as our horizontal distance approaches 0. So as we actually overlap to, again, get back to that secant line. So we're still approaching or using our secant line formula for our slope, but we're applying it to our tangent line to get the instantaneous rate of change at that point x, because our h value, or our horizontal distance, is effectively approaching 0. We're taking the limit as it approaches 0. That is the basis and fundamental concept of derivatives, a very important concept to know in the field of calculus. Okay, that's great. So now let's actually take some derivatives. Okay, let's take the derivative. In fact, let me just erase some of this. I'm going to erase this. We don't really need it right now. And this as well, not really important at the moment. So let's go back to this original function here, y equals x squared. Let's talk about it. Let's say we have the function y equals x squared. I'm just going to draw x squared here. Don't really need the y right now. Say x squared, because of course we only really need y when we're going into implicit differentiation. But that's a topic for a whole other video. Anyways, so we have x squared. We have x squared. That's nice. That's cool. We like that. How do we get the derivative of x squared? Sure, we can plug it in this. And let's do that originally before I tell you about another rule. Okay? So let's take the limit of h approaches 0 of the function x squared. Okay, simple. Let's do that. So we have the limit. I'll try to draw this a little bit smaller so we can actually fit it as h approaches 0 of f of x plus h. But what is f of x plus h? We know that f of x is equal to, well, x squared. So f of x plus h squared should be, well, pretty straightforward. X plus h squared. We're simply squaring our input value, x. And so if you kind of plug that in back here, we get the limit as h approaches 0 of x plus h squared minus f of x, which is just x squared, divided by h. So obviously, as you see here, we can't directly substitute h, or rather 0 in for h, because then we'd be dividing by 0. That's not allowed. We're breaking the rules of mathematics. So we actually expand this out and then cancel out some terms from there until we can actually directly plug in 0 for h. So how do we do that? Okay, simple. I'm going to actually erase this formula right now. You can kind of regard it later on. I might write it later on in the video, but let me erase this too. This isn't really necessary. Okay, so let's expand this term out here. Okay, so let's say this is going to be x squared plus 2xh minus h squared, or sorry, plus h squared minus x squared. And again, we are all dividing this by h. Okay, that's nice. All of a sudden, we see that our x squareds are canceled out. And so, sorry, I forgot to write the limit as h approaches 0, our horizontal distance. Okay, so that's the limit as h approaches 0. So our x squared cancels out here. We don't really need these guys anymore. So simplifying, we get the following. We get 2xh plus h squared over h. Now, I'm too tired to write this down. I'm just going to draw an arrow, kind of demonstrating that we're still taking the limit as h approaches 0. So we still can't directly plug in 0 for h. We still have an h in the denominator isolated. Let's cancel out that h. We see that h is a common factor in both of these terms in our numerator. So let's factor out h. We get that this is going to be the limit as h approaches 0 of h times 2x plus h. Okay, that's cool, and we're dividing by h. All of a sudden, we can remove or cancel out these two h's. So now we're just left with the limit as h approaches 0 of 2x plus h. And now, all of a sudden, we won't be breaking any rules of math if we just plug in 0 for h. So let's do that. We get 2x plus, well, 0, which simplifies to 2x. And believe it or not, we're done with our formula, and the derivative of x squared is equal to 2x. Beautiful. That's exactly the correct answer. But notice how we went through a pretty tedious process of actually using that formula. And there's actually a lot of different rules and theorems you can really apply to find the derivatives of functions. This kind of using limits to find the derivatives is kind of like the base formula. When you don't have any special properties you can use, this is the formula that you'd go with. But in this case, there actually is a very nice and neat trick, or method, rather, to calculate the derivatives of functions with powers. What is that? Let's talk about it. Okay, sorry, I probably shouldn't zoom out here. Let me just erase this. We don't really need this function anymore. And I'm going to zoom in, I promise. I know it's probably a little bit hard for you guys to see. But notice how we did all of this work just to calculate the derivative of x squared. And again, what does 2x actually tell us? This is the slope of any tangent line that intersects the function exactly once. Because again, that is the definition of a tangent line. Alright. Okay, so again, that is the slope of any tangent line that hits the function at exactly 1 point for any value at x, the instantaneous rate of change at any value x in our function. Okay, that's cool. Let me zoom in a little bit. Okay, that's perfect. I think I like this a little bit better. Okay, so now that we have that, now let's talk about the power rule, a very important method here, or rule, I guess, in calculus. What is the power rule? Let's talk about it. So, if we want to find the derivative, which is also represented as d over dx, you've probably seen it a lot. And actually, let's just go over the quick kind of rules or notations for the derivative. So, of course, the kind of base derivative method here is going to be f prime of x. This is the derivative of f of x. And another method here is going to be d over dx, which is what I'm going to be using for simplicity in this video. But both of these methods do completely work. They're both fine. You can use whatever you'd like. Okay, so these are the two notations of how to represent the derivatives of functions. That's great. That's sweet. We like that. Now, what if we wanted to find the derivative, or d over dx, of x squared? So obviously, using our limit method or formula for the derivatives, we already calculated that to be equal to 2x. That's great. But what if we didn't want to do all that work? That's where the power rule comes into play. This is where we have to use that power rule. What does the power rule state? The power rule states that for any d over dx of x squared, the derivative of that, of x to the yth power, that's equal, again, the derivative of that is equal to y times x over, or x to the power of y minus 1. Great. This is true for any derivative of this power. Okay, that's nice. Now, let's see that in action here. So again, we're taking the derivative of x squared. So if we were to directly plug in this function here for that derivative, we'd see that this is going to be a y value of 2, right? Y equals 2, and x is simply x, our input value. Great. So applying that formula, we get that d over dx of x squared is equal to, bringing the 2 down, we get 2 times x to the power of 2 minus 1. This simplifies to 2 times x to the power of 1, which is equal to 2 times x, or 2x. Wow, that's the exact same answer we got when we used our previous formula, but obviously there is a lot less steps and it's a lot less tedious. Okay, let's look at another example. What if we wanted to find the derivative, or d over dx, of 3x to the power of 4? Okay, that's still pretty simple. Bring the 4 down, multiply it with 3, and so we get that this is equal to 3 times 4 times x to the power of 4 minus 1. This is equal to 3 times 4 is 12, times x to the power of 4 minus 1 is 3. This is equal to 12x cubed. Alright, that's nice. Now, I'm just going to put a quick coefficient here of a, so we can have a here as well, so times a, because I forgot to add that. Theoretically, when a is 1, it doesn't really matter, but when we have actually coefficients that are not equal to 1, like this 3 right here, it's important to address that as well. Okay, so we see that we have 12x cubed. That's nice. Let's see one final example. Let's say we wanted to find the derivative of d over dx of 6x to the power of 5. Again, pretty standard derivative here. We simply have to apply that power rule again. This is equal to 6, again, bring that 5 down, times 5 times x to the power of 5 minus 1. 6 times 5 is simply 30, times x to the power of 5 minus 1 is 4. I don't know why that's there. And this is equal to 30x to the 4th power. And that's the derivative of 6x5, or 6 times x to the power of 5. Notice how if we were to plug this into the limit method for the derivatives, it would be a lot more tedious. It would take a lot more time. That's only when you don't have a standard, nice, easy method to solve it, like the power rule or chain rule or product rule and things like that. We're going to get into that later on in future videos, but this is what you need to know about derivatives and differentiation for now. And if you guys enjoyed this video, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.